Okay, so throughout the book, there's a lot of things such that they give, condition one and condition two, and all of that is perfectly fine. Um, it's kind of the same in a calculus book or anything else. I don't want to say ignore it. There's certain definitions, theorems, conditions, things like that, where we're supposed to understand all of it to do the assignment. But if we kind of very easily understand the math, memorize our way through the basic mathematical process, we don't really have to know the conditions, and it's always kind of hard to tell what they're talking about. But we just kind of read this, and we're supposed to define condition one and condition two, but it's more the theory. Yeah. So minimizing costs, we are now ready to tackle the firm's cost minimization problem. The firm has a production function, quantity equals a function of labor and capital, and can use labor and capital at the given prices, wage, and rent. We ask if the firm wants to produce a certain quantity of output Q target at the lowest cost possible. How much of inputs L and K should the firm use? We will call the optimal choices of inputs. Those are the optimal L and K. L star, K star is the optimal L and K. Note that this is a typical constrained optimization problem equivalent to the ones we reviewed in the previous chapter. Therefore, we can directly apply what we learned there to quickly solve this problem. Since we are solving for two variables, L and K, we need two conditions. In the previous chapter, we established that condition one was the optimal choice. Condition one was that the optimal choice must be the constraint. This naturally holds here. The firm wants to minimize its cost, but it wants to produce at least a Q target. Therefore, it does not make sense to produce an output Q bigger than Q target. We are then looking for L and K such that the constraint binds. So that's going to be condition one. So if we understand that, that right there is condition 1, 3.8, we now give it a whirl, condition 2. As before, condition 2 tells us the optimal mix of inputs L and K. This optimal mix depends on the type of production technology of the firm. We will focus on the three main cases: strictly convex isoquants, diminishing marginal return thingamajiggy, linear isoquants, that's the perfect substitutes, and the L-shaped isoquants, perfect complements. They only have those three graphs: the Cobb-Douglas, the straight line linear, and the L-shaped. So strictly convex isoquants, DMRS, definitely the most important. This is the Cobb-Douglas. We only need to reinterpret the logic behind the maximization problem. So we're not going to go through all these figures, but uh, the straight lines in figure 3.9 are different ISO costs. We know the ISO costs. The blue curve is the isoquant for our targeted output. Hence, the firm must choose the point on the blue curve that is on the lowest possible ISO cost. That is a point A in the graph where the curve and the line are tangent to each other. Yes. So, I mean, I understand this here. The way that they say it, doesn't help me out at all. If I kind of read this, it just, doesn't help me that much. But are they going to do it right there? They do it right there. Okay, so I was about to draw it. So this is going to be condition two. Clearly that's condition two, that if you divide the marginal derivatives, it equals W over R. It's just, there's more than one way to write it, but it's just another way of saying if you compare the slopes, it's the point such that they have the same slope. It's also going to be intersecting points. But this is it right here. So we are straight up saying it. If I just go ahead and say something, yeah, we have a desired Q. Yeah, we have a desired output, which is a function of L star, comma K star. So we don't need to be that specific, but all we want is a specific Q star, and it has three things that go with it: the L star and the K star. Okay, so we want to do that. We want the goal of our quantity, our output, and we want to do it while minimizing the cost. Okay, so the production function specifically comes from the Cobb-Douglas. It comes from the isoquant, and it is okay. We're talking differently now, but this is like the third time that we did this. But now we're talking more about what it means. So that thing is the curve is the isoquant, and the isoquant does come from the production function, yes. So we already see it, before I'm done. It's so easy, it's kind of like why continue. But these are all ISO costs such that we have labor and Ks that are all in the same cost. Remember what the ISO cost is. The ISO cost is going to be, it's going to illustrate all possible combinations of L and K such that they have the same cost, but we don't care about that. We care about point A. Point A is going to be where we have the optimal Q that we want while minimizing costs. That's specifically what that's going to be. We have all the Q here, yeah. Yeah, we have all the Q right here. So if we use this cost, let's kind of erase all this here. Just bear this in mind. It's a video, so you can scroll back and forth, but keep this in your retinas here. Yeah. But, just kind of pointing out the obvious, this is an ISO cost. Yeah, this is the quantity that we want. If we use that ISO cost, we're producing the same quantity at a higher cost. So now that we say that, it's very obvious that if this is our isoquant, our desired quantity, remember for all L and Q, I'm sorry, for all K and L, on that line, we have the same Q. We want this one that will give us the lowest cost. So at that point of intersection is the minimization of that. Okay, so very, very easy. And they are saying that that is condition 2. All that previous stuff I read, I understand it my way. I don't really understand it very well when I read through the little thing, but I did just say in better language what they said. So then they say all this here. Okay, so that is the most important one. Yeah. This is kind of take a minute. It's going to be the same for linear isoquants, isocosts, and the perfect substitutes. I'm sorry, perfect complements, the L-shaped isoquants. Yeah, so we can kind of read through this. Feel free to kind of read through this here. I don't really think that we need all of this. But they get down to the point for the linear. Yeah. So the blue line is going to be the isocost. The blue line is going to be the isocost. So if we have a linear isoquant, yes, a linear isoquant, what do we say here? If this is our isoquant, I just spelled that in a weird way. If that's our isoquant, our desired Q, then it's just going to be the point that they intersect, which is always going to be on the K-axis or the L-axis, yeah? Yeah. What if this right here, if this is going to be our isoquant Q, are we allowed to have an isocost down here? I'm not really sure they're giving us that illustration, but they're telling us that it's going to be the point where they intersect. Yeah. So the intersection of the isocost line. Let's kind of scroll through here a little bit before we stop the video. I know that because I kind of make these 10-minute videos or shorter. So then they give us condition 2. Yeah, I think we'll definitely kind of do this in the next video. Yes, but these are going to be the specific conditions. It is a little bit harder to describe that. So we're definitely going to do this in the next video, but they separated into this for the linear. So we'll define that. So the linear is the second most important. The least important is going to be the L-shaped perfect complements. Okay, so we end here, and I think we're going to pick up in the next video here. So let's do that.